This is Dr. D. Govardhan, Professor in Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today the topic is mass moment of inertia, Parallax Theorem. It is also called transfer formula, mass moment of inertia of composite bodies. Mass moment of inertia. The product of mass and the square of the distance between the center of gravity of the mass from an axis, reference axis, is called mass moment of inertia. Here, the example is, let us consider here the body of the mass is represented M. Here C is representing position of the centroid. Then the mass moment of inertia, assume X and Y is representing the coordinates of centroid. The mass moment of inertia of body with respect to the x-axis is given by mass. It is the product of mass and square of the distance between the center of gravity to the reference axis. That means here I is equal to mass moment of inertia is equal to mass into square of the distance equal to y square. Since we have taken the reference axis as the x-axis, generally it is represented as I-axis is equal to my square now. The mass moment of inertia is represented by capital letter I. Sometimes it is also represented by Im now. Hence, mass moment of inertia of the body about the x-axis is represented as Im xx, and about the y-axis it is represented by Im yy as shown in figure now. Mathematically, the mass moment of inertia is represented as the product of mass and the square of the distance between the center of gravity of the body to the reference axis. Hence, with respect to the x-axis, it is represented as now IExx, which is equal to mass multiplied by the square of the distance my square. Similarly, the mass moment of inertia of the body with respect to the y-axis, since the distance is represented in terms of x coordinate, hence Iyy is equal to mass multiplied by the square of the distance, which is equal to m into x square. The perpendicular axis theorem. The moment of inertia of a mass about an axis perpendicular to the plane is also called polar moment of inertia. At any point to O is equal to the sum of the moment of inertia of about the two axes which are perpendicular to each other and passing through the intersection of that axis. Here, let us consider the moment of inertia of a body about the z-axis, which is perpendicular to the plane and passing through the intersection of two perpendicular axes, OX and OY. The moment of inertia of mass about an axis, z-axis, is called here molar moment of inertia. That is perpendicular to the plane of the body. According to the perpendicular axis theorem, the polar moment of inertia of a body is equal to the sum of the moment of inertia about any two mutual perpendicular axes, that is OX and OY, and passing through the same point O and lying in the plane of the mass now. Here, according to the perpendicular axis theorem, OY and OX are the two perpendicular axes which are lie in the same plane of mass, and OZ is representing the axis which is perpendicular to the plane of the mass. The polar moment of inertia is the moment of inertia of the mass about the z-axis, that is OZ, which is equal to the sum of the moment of inertia about the x-axis and y-axis. That is, according to the parallax theorem, mathematically, it is represented as Izz is equal to Ixx plus Iyy. Now, in order to prove this theorem, let us consider an elemental area dm of uniform thickness is at a distance of r from the intersection of x-axis and y-axis as shown in figure. Let dm is representing the mass of the element having coordinates x and y in a coordinate plane as shown in figure. Let I x-axis is representing the moment of inertia, mass moment of inertia of the body about the x-axis, and Iyy is representing the mass moment of inertia of the body about the y-axis, and Izz is representing the mass moment of inertia about the z-axis. Now, according to the Perpendicular X Theorem, Izz is equal to Ix plus Iyy. So, mathematically, Izz is equal to sigma of r square dm, which is equal to sigma into r square is equal to, according to the rectangle, r square is equal to, we can take it as x square plus y square. Hence, r square is equal to sigma of x square plus y square into dm. It is equal to sigma x square dm plus sigma y square dm, which is equal to ix plus iyy. Or in other words, Izz is equal to ix plus iyy. This theorem is called Perpendicular X Theorem for polar moment of inertia. Parallax Theorem. Generally, it is useful for the transfer of mass moment of inertia from central axis to the any other axis which is parallel to the central axis and separated by some distance. For engineering applications, generally the mass moment of inertia, by using Parallax Theorem, it is the most useful to determine the value of mass moment of inertia at a required axis. According to the Parallax Theorem, the moment of inertia about any axis in the plane of an area is equal to the sum of the moment of inertia about a parallel central axis and the product of mass and square of the distance between the two parallel axes. Here let us consider a mass that m is there now. It is concentrated at Cg now. Cg they represent the position of the centroid. Let us consider the mass moment of inertia of a body about a line AB, which is parallel to the central axis GG, as shown in figure. According to the Parallax Theorem, the moment of inertia of a body about AB equal to sum of the moment of inertia of the body about its central axis and the product of mass and square of the distance between the two parallel axes. That is, IAB is equal to IGG plus m by c square. This is the equation. Where IB is representing the mass moment of inertia of the body about the line AB, IGG is representing mass moment of inertia of the body about the central axis, M is representing the mass of the body, and YC is representing the distance between the central axis and the reference line AB. Okay, proof. Consider an elemental parallel strip dm is at a distance of y from the central axis as shown in figure. Let GG is representing the central axis, that means which is passing through the centroid of the body. Let line AB the reference line which is parallel to GG as shown in figure. According to the Parallax Theorem, IAB equal to, that is moment, mass moment of inertia of the body about a line AB is equal to IG plus, that is sum of the mass moment of inertia of the body about central axis and mass into square of the distance between the two parallel axes, that is m by c square, where yc is representing the distance between the central axis and the line AB. Now, in order to prove this equation, let us consider a small strip of mass dm at a distance of y as shown in figure from the central axis GG now. The mass moment of inertia of small strip dm about a line AB is equal to the product of mass and the square of the distance between the center of gravity of the small ship dm and the line AB now. That means IAB is equal to sigma of y plus yc whole square into dm. Since it is in the form of a plus b whole square, it can be written as now sigma of y square plus 2y yc plus yc square into dm. Again, on expanding, we got sigma y square dm plus sigma of 2y into yc dm plus sigma yc square dm. Sigma y square dm is representing the mass moment of inertia of the body about its centroidal axis, hence it is represented as IgG now. That means this term is equal to IgG now. That is mass moment of inertia of the body about its centroidal axis. It is represented as now IgG now. The second equation is 2 sigma of 2y yc dm. This equation can be written as 2yc into, because 2 is the constant of yc is also constant. Hence, the remaining terms are sigma y into dm. Here, in these equations, we are multiplying the mass in denominator and numerator. We got the values 2yc, here m, sigma y dm divided by sigma dm now. The sigma dm is representing the total mass of the body, hence here represented numerator as m only. Here m is the constant, 2 is the constant, y is the constant. The remaining terms can be represented within the bracket like this, sigma y dm divided by sigma dm. This is representing the position of the centroid with respect to the central axis or the reference line GG now. But it is the centroid, it itself is coincident with the GG values now, GG axis. Hence, the term sigma y dm divided by sigma dm, these values are treated as 0 now. Hence, the term 2yc into m, the remaining value is equal to 0. Hence, the middle term is also equal to 0 now. The remaining terms is there now, third term, sigma yc dm now, where yc is the distance between the parallel lines GG and AB, it remains constant, hence yc is the theta constant. The term sigma dm is representing total mass of the body now. Hence, sigma yc square dm, it can be written as myc square as shown in the equation now. Hence, IAB is equal to now IgG. The third term, the second term in the middle term is treated as 0. The remaining term is myc square now. That means IAB is equal to IgG plus my square. This is known as Parallax theorem. That means the Parallax theorem, it stated that the mass moment of inertia about any axis in the plane of an area is equal to the sum of the moment of inertia of the body about its central axis and the product of mass and square of the distance between the two parallel lines. The moment of inertia of a uniform rod. Now consider uniform thin rod AB of length as shown in figure. Now here to find the position of the mass moment, we have to find the moment of inertia of the rod about the line YY as shown in figure. Let M is the representing the mass per unit length of the rod. Hence, total mass of the rod is represented as now capital M, which is equal to the product of M into L, where M is equal to represent the mass per unit length of the rod now. Now consider small strip which is at a distance of x from the reference line y as shown in figure, having length is equal to dx now. Then mass of this strip is equal to m into dx, because we are considering a length is equal to m into dx only. That is dx only. M is representing the mass of the rod per unit length now. Hence, mass of this strip is equal to, it is represented as now small m into dx now. The moment of inertia of this strip about the y-axis is equal to mass multiplied by the square of the distance. Mass is equal to m into dx. Square of the distance is equal to x square now, which is equal to mx square into dx now. The moment of inertia of the whole body or entire thin rod about the y-axis is obtained by integrating these equations from the limits from 0 to L now. That means Iyy is equal to 0 to L into mx square into dx, which is equal to m is a constant and x square dx integration is equal to x square by 3. Limits are 0 to L, which is equal to ml cube divided by 3. But m into L is equal to, that is lowercase letter capital mass is equal to m into L, where a small letter m is representing mass per unit length, L is equal to length of the body, hence the remaining letters are ml square by 3. This is the representing the mass moment of inertia of uniform thin rod about its one end. That is about y-axis now. Now mass moment of inertia of a rectangular plate now. Here consider rectangular plate having breadth is equal to b, depth is equal to d, and uniform thickness t as shown in figure. Let the x-axis is representing the horizontal line, which is passing through the bottom of the figure, and the vertical axis OY is represented the extreme left of the given body. Now consider a small element of dy, here which is represented here now, of dy, having uniform thickness dy at a distance of y as shown in figure now. The area of the strip is equal to breadth multiplied by the thickness, that is b into dy as shown in figure now. Let rho be the representing the density of the materials and t is the uniform thickness, hence the mass of the element, mass of the strip is equal to, that is density multiplied by the volume of the material. Volume is equal to area into thickness, b dy into t, that is equal to rho t b dy now. The mass moment of inertia of that strip, that element strip, about the x-axis is given by mass multiplied by the square of the distance. Since it is at a distance of y from the x-axis, hence mass is equal to rho bt dy into y square, rho t b y square dy now, where rho is representing the density of the materials, b is representing breadth of the materials, t representing the thickness of the materials, and dy is the thickness of the strip considered, which is at a distance of y from the x-axis. Then the mass moment of inertia of the entire body about the x-axis is obtained by integrating these equations now from 0 to d now. Hence ix is equal to, we can take it as rho t, that are constant now, 0 to d, by square into dy, that is rho t b, that is 0 to d, y square dy. Again rho t b is there now constant, so y square dy integration is y cube by 3, and applying limits from 0 to d, the values are rho t b d cube by 3 or rho t b d cube by 3, where rho t b d is representing the mass of the body, the remaining terms of d square by 3 now. Hence this equation can be written as m d square by 3. This is the representing mass moment of inertia of the strip about its base, it is represented by m d cube by 3 now. Similarly, the mass moment of inertia of the body about the vertical axis now, that is Iyy is equal to, it can be written as now mb cube by 3 now. mb³ by 3 now. Now the distance between the central gravity. Now let us consider the moment of inertia of the body about its central axis now. That is gg. Now according to the parallax theorem, IAB is equal to, that is moment of inertia of a body about the base AB, it is equal to IG, that is moment of inertia of the body about the central axis, plus the product of mass and square of the distance between them. Generally it is represented as h1 square now. This is known as Parallax theorem. From this relations, I can write Ig is equal to IAB minus mh1 square. This principle is useful for us for determining mass moment of inertia of the body about the centroidal axis, which is equal to, here according to the Parallax theorem already told, Ig is equal to Ixs minus mh square, which is equal to Ixs is equal to, already we determined the value is equal to md by 3, and m, the h1 is it is equal to half of the depth, which is equal to d by 2 whole square, or in other words md³ by 3 minus md square by 4. So the 12 is the LCM for the equations, and so the remaining values is 4 md square minus 3 md square is equal to md square divided by 12. This is known as the mass moment of inertia of the body about its centroidal axis. Similarly, the mass moment of inertia of hollow rectangular plate now. Let us consider capital B is representing the breadth of the outer rectangle, capital D is representing depth of the outer rectangle, and small b and d are representing corresponding values for the cutout rectangle, and assume the plate is having uniform thickness T now, and the density of the material is rho. The mass moment of inertia of the rectangle ABCD about an x-axis, that is, here the x-axis is representing the central axis, the axis which are passing through the centroid, and parallel to the x-axis is represented here x-axis. The vertical line which is passing through the centroidal of the body that it is the y-axis now. So we are taking the mass moment of inertia of the hollow rectangle about the central axis, I-axis is equal to, according to the equation we are having md³ by 12, so which is equal to, m is equal to the density multiplied by the volume rho t bd. This rho bdt is representing the product of breadth, depth and thickness. It is known as volume multiplied by rho, it is called mass now, d square by 12 now. Here where d is nothing but representing the depth of the outer rectangle. The mass moment of inertia of the cutout rectangle, again about the x-axis, it is given by rho t bd d square by 12. Here we are using lowercase letters to represent the dimensions of the cutout rectangle now. Then the mass moment of inertia of the hollow rectangular section about the x-axis is obtained by the difference of the mass moment of inertia of outer rectangle and the mass moment of inertia of cutout rectangle EFGH. Hence on subtracting we got now rho t bd d square by 12, rho t bd d square by 12, which is equal to here now mb square by 12 minus half mb square by 12, where b is representing the here breadth of the outer rectangle, and the lowercase letters b is representing the breadth of the cutout rectangle. These relations hold good. The central of gravity of the inner rectangle and outer rectangles both are constant with each other now. Moment of inertia of a circular section. Now let us consider a plate of circular section having uniform thickness d, and capital D is representing the diameter of the circle, and capital R is representing the radius of the circle. Let the axis x dash is representing the central axis, which is passing through the center of the circle and in horizontal directions. Similarly, y is representing the central axis in the vertical directions. And z it is representing the axis which is passing through the center of the circle and perpendicular to the plane. Hence, the moment of inertia about the z-axis here it is polar moment of inertia. Now let us consider ring which is at a distance of r from the center of the circle, having thickness dr as shown in figure now. The area of the strip is equal to given by area of the strip. Generally it is equal to dA. It can be written as 2 pi r and dr now. Since it is having uniform thickness T and rho is the density of the materials, the mass of the elementary strip is equal to, it obtained rho T 2 pi r and dr now. So it can be written as now 2 rho T pi, these are the constant, the remaining 2 r into dr are the variables. So the mass moment of inertia of the entire sections, that is entire circular plate which is having uniform thickness about the z-axis Izz is given by integrating these equations from the limits from 0 to r now. That is 0 to r rho T 2 pi r cube dr now, which is equal to rho T, because here it is nothing but area, it is a mass. That is mass moment of inertia small element is equal to, we can take it as 2, that is the mass multiplied by the square of the distance is equal to r square now. That is dou m into r square. Dou m is equal to rho T 2 pi r dr, and the square of the distance is equal to r square, which now become 2 pi r cube dr now. Since rho T 2 pi are the constant in the equations, the remaining terms 0 to r integration r cube by dr, on doing integrations rho T 2 pi r to the power of 4 divided by 4, the limits are 0 to r now. Or Izz is equal to rho T pi r to the power of 4 divided by 2, r which is equal to mr square by 2, r which is equal to, when substituting r is equal to d by 2, we are having this value is equal to md square divided by 8 now. Okay, this is the equation generally used to determine the polar moment of inertia of circular uniform thickness plate now. But according to the Parallax theorem, Ixx plus Iyy is equal to Izz, or Izz is equal to Ixx plus Iyy, and this plate is uniform, symmetrical about the x-axis and y-axis and having equal values. Hence, Ix is equal to, it is written as Iyy, which is equal to Izz by 2 now. Hence, Ix is equal to, it can be written as md square by 16 now. Moment of inertia of a hollow circular section. Now let us consider a hollow circular section, the plate which is having uniform thickness T, and capital D is representing the diameter of the outer circle, it is also called main circle, and small d is representing the diameter of the cutout circle, which is shown in figure now. Let us consider the plate is having uniform thickness T now, and the density of the material is represented rho now. So according to the fundamentals of previous equations, Izz is equal to, we are having mr square by 2 now. Similarly, Izz is equal to, it can be written as now mr square by 2 now. Izz is equal to, Ixs is equal to, it is equal to Izz by 2 now. That is mr square divided by 4. When we are representing r is equal to d by 2, it can be written as now m d to 4 of m d square divided by 16 now. So this is nothing but representing the Ix is equal to md square by 16 now. Similarly, the mass moment of inertia of cutout circle about the x-axis, that is the horizontal axis, given by md square by 16 now. So the mass moment of inertia of allo circular section about the x-axis given by the difference of inertia of outer circle and the inertia of cutout circles, which is equal to md square by 16 minus of md square by 16. 16 is the common, hence 1 by 16, that is m by 16, d square, capital D square minus small d square. This is known as mass moment of inertia of allo circular sections about the x-axis, and also which is passing through the center of the circle, that is the central axis. These equations holds good when the center of gravity of the main section as well as the cutout sections both are coincident with each other. Moment of inertia of triangular section. Here consider a triangle having base is equal to b and height is equal to h, having uniform thickness as shown in figure now. Like this. It is having uniform thickness. Which is represented here now, uniform thickness like this. Now, consider, in order to determine the mass moment of inertia of triangular section, which is having breadth is equal to b, height is equal to h, and uniform thickness t, and the material density is represented here rho now. Now consider a small strip PQ, which is at a distance of y from the base as shown in figure. Here the PQ is there, which is at a distance of y from the base BC now. Now let us consider the mass moment of inertia of this about the line base, about the line BC, which is equal to the, that is I am taking di, that is the mass moment of inertia of the strip about the line BC, which is equal to mass of the element, assume dm, multiplied by the square of the distance. So in order to determine the dm value of this small strip PQ, we have to consider the fundamentals of similar triangle principle. Here A, B, C and the triangle APQ both are similar now. When they are similar, the ratio of lengths of corresponding sides should be equal. That means according to this figure, PQ divided by BC is equal to PQ divided by BC is equal to, here the height of the APQ line is given h minus y, that is h minus y by h now. That is PQ divided by BC is equal to h minus y by h as shown in figure. That means PQ is equal to, BC is equal to, already we assumed it is equal to breadth of the base B now, hence B into h minus y divided by h now. From this relation now, the area of the strip is equal to PQ into dy, which is equal to B into H minus Y by H into dy. So moment of inertia of this tip about the line BC is given by the product of mass multiplied by the square of the distance between the PQ and the baseline, which is equal to mass of the element is equal to area is already we determined, which is equal to B by H into H minus Y dy. In order to get the mass, it should be multiplied by the thickness, that is give the volume, and multiplied by the density, that give the mass. That means just to multiply by rho and T and the area. This is equal to rho T B by H minus Y into dy, and the square of the distance in order to get the mass moment of inertia is multiplied by the y square. That means the mass moment of inertia of this element PQ about the line BC is obtained. That is the mass multiplied by the square of the distance. That is rho T into area multiplied by the distance between the PQ line and BC line, which is equal to rho T into B into H minus Y by H into dy into square of the distance is equal to y square. Okay, on simplification, so rho T B by H, they are the constant terms. So that is rho T into B by H constant terms. The remaining terms on expansion gives H y square dy minus y cube dy. The mass moment of inertia of entire triangular section about the line BC is obtained by integrating this equation number 1 within the limits from 0 to height of the triangle H now. So, I am doing integration now. That is rho T into BH, 0 to H, Hy square dy minus y cube by dy. Here rho T into B by H, these are the constants now. So, Hy square dy integration is Hy cube by 3 minus y cube dy integration is y to the power of 4 by 4 now. So, applying the limits from 0 to H, we got rho T by H is the constant, H4 divided by 3 minus H4 by 4. Here 12 is the LCM for these two terms now. And so the remaining values rho T into BH is the common term. The remaining value is 4 H2 to the power of 4 minus 3 H2 to the power of 4, which is equal to rho T BH to the power of 4 by 12 now. So in these equations now, so HH get cancelled, the remaining values rho T B H cube divided by 12 now. Here rho T is the constant. Here we are converting the area of the triangle is equal to half of the product of base into height now, which is equal to half into B into H. The remaining terms H square by 6. So the rho T and area, this is equal to area. This is called mass of the body into H square by 6. It can be written as mH square by 6. This is known as mass moment of inertia of triangular section, which is having uniform thickness T about the BC. It is given by mH square by 6 now. Okay, sometimes it is also required to determine mass moment of inertia of the triangular section about its central axis. Here central axis is nothing but the axis which is passing through the centroid. Here we are taking parallel to BC, as in this is represented as IXX, or sometimes it is also represented as IGG also now. Now, according to the parallax theorem, IAB is equal to, that is the mass moment of inertia of triangular section about a line BC. It is equal to IG plus mass into square of the distance between these two lines, as in it is equal to H1 square now. But the center of gravity of the triangular section lies at a distance of h by 3 from its base now. That means I can take h1 is equal to h by 3 in that equations. So from this relation we got to Ig is equal to IBC minus MH1 square, where h1 is equal to h by 3, where h is representing the height of the triangle. So by using these relations, mh square by 6 minus of m into h by 3 whole square. This is equal to mh square by 6 minus of mh square by 9. On simplification, we got this value is equal to mh square by 18. This is obtained by using the principle of parallax theorem. Similarly, the mass moment of inertia of semicircular section. Let us consider semicircular section having uniform thickness T and the density is equal to rho, and the RB is representing the radius of the semicircle. The mass moment of inertia of semicircular plate about its base is obtained. It is equal to the half of the moment of inertia of the circular plate now. That means which is equal to, that is IAB is equal to, we are having rho T, that is pi d square by 2 now, divided by 64 now. That is we are having md to the power of md square by 64 we are having. So which is equal to now, m is equal to rho T into pi d square by 2 divided by 64. Here which is equal to rho T into md square by 4 into d square by 32, which is equal to md square by 32 now. Here we are taking m is nothing but representing the mass of the element now. The mass is equal to rho T into area is equal to pi d square by 4. Here this is nothing but we have to take half circle, that is 1 by 2 into pi d square by 4 divided by 64 now, which is equal to, now you can take it as rho T is nothing but representing the, rho is representing T density, T is representing thickness, area, hence this is equal to, we can take it as that is the mass. The 2 T is there now, that is 32, that is d square by 32. This is representing the mass moment of inertia of the semicircular section about the diameter AB now. The product of inertia and transfer formula. The product of inertia, it is explained mathematically as let dA is representing the mass of the element, just having coordinates according to the xy planes, x and y as shown in figure now. Then the product of inertia of this area dA is defined as the, that is small area, dxy is equal to area multiplied by the square of the distance. The square of the distance, instead of writing the square of distance, it is nothing but a product of x coordinate and y coordinate. That is the product of inertia of an area. It is equal to area multiplied by the coordinates of x and y with respect to the reference axis. So the total product of inertia possessed by the area is given by integrating this equation. So that is the Ixy is equal to, taken as the area multiplied by the integration of, that is the xy dA now. Okay, this is known as the product of inertia for the entire area. That is the area multiplied by the product of x coordinate, y coordinate with respect to the two reference lines as shown in figure now. Okay, transfer formula for the product of inertia. Here, the moment of inertia about any other line now, which are parallel to the x-axis and y-axis as shown in figure, it is represented by Ixy. It is equal to ij x dash y dash plus a into hx and hy now. Ij xy dash y dash is representing this moment of product of inertia with respect to the central axis, and hx and hy is representing the distance of centroid with respect to the x-axis and y-axis as shown in figure. Mass moment of inertia of solid cone. The mass moment of solid cone. Here, the solid cone it is having in the form of right circular. That is, the axis is always perpendicular to its base now, as shown in figure. Let us consider the mass moment of inertia of cone about a line which is perpendicular to the axis and passing through the apex as shown in figure. Here it is represented as Z now. The mass moment of solid cone of ITH and the base radius R about the axis of rotation. Now let us consider a small strip of circular plate at a distance of x having thickness dx as shown in figure now. Since the axis is here symmetrically about the x-axis, hence the axis of rotation x-axis into the x-axis and y-axis and z-axis and so on. It is represented. The moment of inertia of let r be the representing the small r is representing the radius of the azimuth circle which is at a distance of x having thickness dx as shown in figure now. Now if it is in the form of like this, if we take this above this one, this is the referent axis now. Here according to this figure O, if it is A and B, we will take it. This is represented as A and it is represented as axis and so on. Here somewhere I am taking A dash now, which is given R and capital R, and this distance is given here length of the axis. This distance we are considered x now. These two are the similar triangles. That means according to the figure, we are having R by capital R is equal to, it can be done x by h now. Or from this relation, so R is equal to capital R divided by h into x now. Okay, which is represented here in these equations now. The mass moment of inertia of this circular lamina, which is having thickness dx about the x-axis, that is the axis is nothing but passing through the center of the circle, hence which is equal to the mr square by 2 now. Now the density where m is equal to the mass of the element, which is equal to the density multiplied by the volume into r square by 2 now. Let us consider r is rho is representing the density of the materials now, and area is equal to area multiplied by the thickness. The area of the plate is equal to pi r square, and the dx is representing the thickness of the elementary area, hence it is equal to pi r square into dx, so r square by 2 now, which is equal to rho into pi r to the power of 4 into dx by 2 now. But here r is equal to, we can take it as r by h into x now, and substitute the values of r is equal to r by h into x in this equation number 1. We are having 1 by 2 into rho pi into r to the power of 4 divided by h to the power of 4 into x to the power of 4 into dx now. Then the mass moment of inertia of that entire cone about the z-axis, about the x-axis given by doing the integration from the 0 to h. So about the x-axis given by 0 to h, 1 by 2 into rho into pi into r to the power of 4 by h to the power of 4 and x is 4 dx now. So which is equal to 1 by 2 into rho pi r to the power of 4 divided by h to the power of 4, x to the power of 5 by 5 now. Okay, and applying the limits now, we got to 1 by 2 into rho pi r to the power of 4 Here h power 4, h power 5 get cancelled. The remaining values is equal to h by 5 now. Since the area of the cone is given by 1 by 3 pi r square h, this is known as the volume. When it is multiplied by the rho, it gives the mass of the cone now. Hence 1 by 3 into rho pi r square h, just multiplying divided by 3 we got taken now, and the remaining values is r square by 10 now, because 2 into 5 is equal to 10 now. So it is equal to 3 by 10, that is mr square. It is representing the mass moment of inertia of the cone about the axis OX according to that figure now. Okay, these are some of the fundamentals of mass moment of inertia of regular objects now. The circular disk is already told, Rx is equal to mr square by 4 and y is equal to mr square by 4, z is equal to, that is Iz is equal to Ix plus Iy, both are equal, hence it is equal to mr square by 2 now. For the sphere now, Rx is equal to, since it is symmetrical about the x-axis and y-axis and z-axis, hence it is equal to 2 by 5 mr square now. Okay, these are the important terms just you have to note down for solving certain problems. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.